welcome to my YouTube channel. If you're just new here, kindly hit subscribe. Our next discussion will be here to discuss a course review of pre-calculus. So we'll talk about a review of the following topics: relation and function, interval notation, domain and range, operation on functions, and composite functions. Okay, let's start. What's the difference between relation and function? Relation and function are interrelated with each other. So to define, a relation is a set of ordered pairs of mathematical quantities, while a function is a special type of a relation such that no two distinct ordered pairs have the same first number. Meaning to say that every function is a relation, but not every relation is a function. Okay, so the following are relations, but the first set of mathematical quantities, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, is a function. If we take a closer look with the mathematical quantities present here, notice that no first number is being repeated. Every pair of number has a distinct first number. For the next example, 2, negative 8, 1, negative 4, 0, negative 2, 0, 2, 1, 4, and 2, 8 is not a function. So if we will notice, there are ordered pairs which have the same first number, like 2, negative 8 and 2, 8. We also have 1, negative 4, 1, 4, and 0, negative 2, 0, 2. So this is a relation, but it is not a function. Okay, so for interval of real numbers is defined as the set of all real numbers between two given numbers, that is, the endpoints of the intervals and one, both, or neither endpoint. For interval notation, we have three classifications. First one is open interval, denoted by an open parenthesis, the two endpoints, and the closed parenthesis. This means that if we have an open interval, it includes all real numbers between but not including A and B, such that A is less than B. So we write first a smaller number before the larger number. Okay, for the closed interval, it is denoted by an open bracket and then two endpoints and the closed bracket. So if we have a closed interval, this includes all real numbers between and including A and B. And then take note that A is always less than B. Okay, the third interval notation is what we call the half open or the half closed intervals. It is denoted by a combination of an open parenthesis and a closed bracket, or open bracket and a closed parenthesis. In each case, the interval contains one endpoint but not the other. Okay, let's consider the following examples. Find the interval when x is greater than 3 and x is less than 8, where x is an element of the integers. Okay, so this means that x is greater than 3 but less than 8. Therefore, it includes the whole numbers greater than 3 but less than 8, which are 4, 5, 6, and 7. Thus, the solution set is the open interval 3, 8 or the closed interval 4, 7. Okay, another example. Find the interval given negative 2 is less than or equal to x but is less than or equal to 4, where x is an element of the real numbers. This includes the numbers in between and including negative 2 and 4, which are negative 2, negative 1, 0, 1, 2, 3, 4, including those in between, such as negative 1.5, 0.3, 1.25, and so on. So thus, the solution set is the closed interval negative 2, 4. Another example is find the interval when x is less than or equal to 0 but is less than 5, where x is an element of the real number. So the interval is closed at 0 because of the inequality sign, less than or equal to, but it is open at 5. So thus, the half open or half closed interval is 0, 5. So it's closed at 0 but open at 5. Okay, so let's proceed to the domain and range of a given relation. But first, let's define what is a domain of a relation and the range of a relation. So for the domain of a relation, it is the set of first coordinates of the ordered pairs of a given relation, while the range of a relation is the set of second coordinates of the ordered pairs of that relation. Meaning to say that the domain of a relation is the set of abscissas in a given ordered pairs, while the range of a relation refers to the ordinates of a given set of ordered pairs. For example, A is a set of ordered pairs, negative 2, negative 1, 2, 1, negative 1, negative 2, 0, 3, 1, negative 2, 1, 2, 2, negative 1, 2, 1. So in here, A is just a relation but it's not a function. Can you tell me why? Yes, because there are ordered pairs which have the same first number. The domain is the set of all the first coordinates of the ordered pairs, while the range is the set of all second coordinates of the ordered pairs. Thus, the domain represents the set of negative 2, negative 1, 0, 1, 2, while the range includes the following numbers: negative 2, negative 1, 1, 2, 3. Notice that in the arrangement or in writing domain and range, we must arrange the numbers in a given set in ascending order. Ascending means it's increasing. So we'll start first with the least value up to the greatest value. Okay, let's have another example. Determine the domain and range of the relation defined by x is equal to y squared plus y. So to find the domain and range in this given equation, we first assign values for y, then solve for x using this value. So why do we have to assign first for the values of y instead of x? Since the equation is implicitly written in terms of y, then we must assign first values for y and then solve for x using the values we assign for y. Meaning, if we have y equals negative 3, then if we replace y in the given equation with negative 3, we could have x is equal to 6. If y is negative 2, x is 2, and so on and so forth. So you may also check the value if these are correct. Okay, so in this sense, if we look at the set of given numbers for x, even if we have a negative value for y, the abscissa is impossible to have a negative number. So it is closed at 0. While for the range, it includes all real numbers from negative infinity to positive infinity. Okay, so we take a closer look to a function. So a function f is a special type of a relation such that no two distinct ordered pairs have the same first number. And then we use the symbols f, g, and h to denote functions. So consider this figure. So the left being here represents the domain with the given elements A, B, and C. And then it is mapped to another given set, which is our range, to form the function y equals f of x. So A is mapped to f of A, B is mapped to f of B, and C is mapped to f of C. Notice that every element in the domain is assigned with different value in the range. Also, notice that any element in the domain, it's never assigned to more than one value in the range. But if in case A is also mapped to f of B of the range, then this can never be considered a function. Okay, let's have another example. So we have here the set in the left, which includes the elements A, B, and C, and it is mapped to another set of elements f of A, f of B, and f of C. Notice that each element in the left figure is assigned to their corresponding values in the right. However, both A and B are mapped to f of A, while C is mapped to f of C. But still, this relation can also be considered a function because there is no element in the left side that is mapped twice to any element in the right side. In symbols, we use y is equal to f of x, which is read as y is a function of x, where y is the dependent variable and x is the independent variable. We also say that y is expressed explicitly in terms of x, since we could readily solve y in terms of x. An implicit function is not expressed in terms of a single variable. So all we have to do is to perform algebraic manipulation in order to solve for y in terms of x or x in terms of y. Okay, 2x plus 3y equals 6 is an implicit function, but if we solve for y in terms of x, then we express it as an explicit function. That is, y is equal to negative 2 thirds x plus 2. Take a look at this example. If f of x is equal to 3x minus 1, find f of 2, f of t, and f of t plus 1. So this means that we have to replace x with whatever is inside the parentheses. So the first example, we have to replace x with the real number 2, such that 3 times 2 minus 1 is equal to 5. Therefore, f of 2 is equal to 5. Next, f of t. So we have to replace x with any arbitrary variable t. So f of t is equal to 3t minus 1. Well, for the last example, we have to replace x with t plus 1, such that 3 times t plus 1 minus 1, or that is equivalent to 3t plus 2. Okay, let's have another example. So given that f of x is equal to x squared, find f of 2, f of h, f of k plus 5, and f of k plus h. Just like with the first example, we need to replace x with whatever is inside the parentheses. So f of 2 is equivalent to 2 squared, which is equal to 4. For f of h, let's just replace x with h such that it will become h squared. And then for f of k plus 5, we have to replace x with k plus 5, and then we expand the given binomial such that k plus 5 quantity squared is equal to k squared plus 10k plus 25. While for the last, we have f of h plus k, meaning to say that we have to replace x with k plus h. But since if we have to arrange the given variables in alphabetical order, we must write first h before k. That's why we have here h plus k. And then we expand the square of a binomial h plus k. Hence, we have f of h plus k is equivalent to h squared plus 2hk plus k squared. Next, we have the operations and functions. So in operations and functions, we just have to perform addition, subtraction, multiplication, and division of polynomials. So we have to consider the laws of exponents, laws of radicals, and other properties of real numbers that can be applied in this algebraic manipulation. Okay, so given the two functions f of x and g of x, their sum, denoted by f plus g of x, is defined by f plus g of x is equal to f of x plus g of x. To get their sum, we just have to add whatever the function we have for f of x and g of x. So for their difference, it's just the same as subtracting polynomials, wherein we change the sign of the subtrahend. While their product, denoted by f dot g of x, is defined by f dot g of x is equivalent to f of x times g of x. So we just have to multiply the two given functions. While for their quotient, denoted by f divided by g of x, is defined by f divided by g of x is equal to f of x over g of x, where g of x is not equal to 0. Note here that the restriction g of x is not equal to 0 is very important to make the quotient of functions defined. For composite functions, given two functions f and g, the composite function denoted by FOG is defined by FOG of x is equal to f of g of x. And the domain of FOG is the set of all numbers in x and the domain g such that g of x is the domain of f. Meaning to say that whatever is the domain of g of x will be included in the domain of f. Okay, let's have this example. Given f of x is equal to 5 over x minus 2 and g of x is equal to 2x plus 1, find the FOG of x. So using the formula, we have FOG of x is equivalent to f of g of x. So we have to replace g of x here with the equivalent function that is 2x plus 1. And then, since we have f of x is equivalent to 5 over x minus 2, we have to replace x here with whatever is inside this closed bracket. So we have 5 over x is replaced with 2x plus 1 minus 2. And then, performing algebraic manipulations, we have 5 over 2x minus 1. Okay, let's have another example. So what if we are asked to compute for FOG of 3? So since we have determined the value for FOG of x, which is 5 over 2x minus 1, we just have to replace x here with the value 3. So that 5 over 2 times 3 minus 1 is equivalent to 5 over 5 or 1. So it is always important to remember the restriction for the denominator to be not equal to 0 to make the resulting equation be defined. That's all for this session. See you next time, and if you have further questions, I will entertain them in our next meeting. Good day! Bye-bye!